Hello, everybody. Welcome back to Calculus 3. This time, this video is on section 4.8, which is the last section of chapter 4. And section 4.8 is going to be rather short. This is about one topic which could be optional. And so this topic is called Lagrange's multiplier or Lagrange multipliers. And it's a method that Lagrange came up with concerning optimization. So this is yet another somewhat a very cool method of finding maximum and minimum points due to Lagrange. All right, so let's get to it. All right, so lesson 8, section 4.8, as I just mentioned, this is on Lagrange multipliers. Who in the world is Lagrange? He's got like 5 or 6 different first and middle names. Lagrange, born in Turin, Italy, in the late 1700s, was as a mathematician, Italian-born mathematician who I believe immigrated into France. And he was one of the major players in the math and science, mathematical and scientific developments in the late 18th and early 19th century. All right, so you will probably hear his name in other science and math classes as well. And his idea, and I said this is another and yet cool method for optimization. And I think you'll agree with me by the end of this section that it's really cool. All right, so what's so cool about this? I'm going to give you an illustration from Calculus 1, all right, and then try to apply that in the context of Lagrange multipliers and see how this works, all right? So let's get started on this first and a very simple problem that you would have seen in Calculus 1. All right, suppose there's a river, okay? You can almost imagine what kind of question I'm going to ask you here, right? Because in Calculus 1, you had this optimization problem. I'm sure you've seen this before, right? So you want to build a fence to enclose a rectangular region by the river. So one side is missing. You don't need to have a fence on the side of the river. And so the idea is to maximize this area surrounded by the fence. All right, let's say you have a fencing material, which is going to be 1,200 feet long. And so you have to provide x plus y plus x. That is, you are supposed to maximize the area. And of course, the area A is xy. All right, and the subject or subject to the constraint, this is a typical way of saying it. It's typical language when you talk about optimization problem, maximizing or minimizing problem. So you are trying to maximize or minimize a function, in this case, the area, which is x times y, subject to the constraint, blah, blah, blah. All right? And in this case, the constraint, of course, is 2x plus y. That's the total length of this fence, has to be 1,200. It's actually less than or equal to, but of course, if you're trying to maximize the area inside, then you want to make sure that it is exactly 1,200, right? And so this is an easy question. You know, what you have to do is to write y in terms of x, that's 1,200 minus 2x, right? And then you plug that into the area you're trying to maximize. Right now, the area is a function of x and y, but you can write this strictly in terms of x, which is x times y, but y can be written now as 1,200 minus 2x, and so you can write this as negative 2x squared plus 1,200x, or you can just use this as is, right? Because you know that this is a quadratic function with a negative leading coefficient, which means that you have a parabola. Right, this is x and this is a of x, and the parabola is downward. And in fact, this factored form tells you that 0 and what is that? 600? Yeah, 0 and 600 are the zeros or the x-intercepts of this function a. right? And so the graph has to go like this. And without even knowing calculus, I mean, you can do this in the pre-calculus class because you know the vertex has the x coordinate of what? Negative b over 2a. And that's something you learn like in the college algebra or pre-calculus class. And the answer must be 300, okay? Or you can just take the derivative and find that the maximum must be 300 because this is negative 4x plus 1200. Set that equal to 0. X has to be 300. The second derivative tells you that it is, the second derivative is negative, and therefore it must be a local maximum, in this case, the global maximum, assuming that, well, and with, I guess with or without the fact that x has to be between 0 and 600. See, if x is 600, you have, 600 here and 600 here, and y has to be 0, right? Because the total fence length is 1200. And if y is 0, you basically have no area. And so that is when x is equal to 600 or 0, the area turns out to be 0. All right. And the maximum area in this case will be what? 12, let's see, it is 300 times 1200. Actually, what's y? Y is, according to this equation, okay, according to this equation here, y is 1200 minus 600, so it will be 600. Basically, what we have found is when the area is 300 by 600 feet, then it'll have its maximum area, which turns out to be 180,000 square feet. Okay, that is a problem in Calculus 1. Or pre-calculus, no problem, right? All right, so here's what Lagrange, in his genius way, thought about this problem, okay? What he did is to think of this constraint. Let's see, we don't have a name for a constraint. Let's see, this constraint is g of xy. The constraint is often described as a lowercase g, okay? Now, if you think of 2x plus y is equal to 1200, that's basically a line, right? And so the line in terms of x and y is like this, where 1200x. Actually, let me redraw this, make it a little bigger for better clarity. Okay, so Lagrange's idea, and again, I don't know how he came up with it. This is just so brilliant, How did these people come up with these ideas? Can we come up with some great ideas and, leave our name as a method of, integration or optimization forever for the rest, for the future generations? I don't know. Maybe you can, right? I mean, it's great when you have this bright kind of a new idea that would forever be remembered with your name. But Lagrange's idea was this, okay? Suppose you have this x and y coordinate plane, and g, the constraint can be thought of as a line, right? This red line that you see here, okay? Now, you are to maximize what? Maximize this function, which is basically xy, okay? And without rewriting y as a function of x, I mean, this is just the area, right? Consider the level curves. Level curves of f. So f, which is xy, is just k, right? And so y is equal to k over x, and you can, you can imagine, or you can just figure out this is what? I mean, what kind of a curve is this? Based on, depending on what k is, if k is 1 or 2 or 3, whatever k is, it's going to be an hyperbola, all right? An hyperbola that kind of goes through like this, okay? And of course, you have another component over here. I mean, that's what this is. We say y is inversely proportional to x, right? And k is called the constant of that inverse proportionality. All right, and so that's what happens here. If k is, for instance, 100,000, it goes through this point and this point, and then as k gets bigger, and this goes a little further away like this, right? Maybe here k is 160,000. Okay, and so what we are saying is basically, and I think you can picture this. Okay, so the answer has to satisfy g, right? In other words, the answer is going to be some point in G. But if you pick this point or this point, okay, then K, the area is only 100,000. And then here and here, it's 160,000, okay? And you can draw another one here. That would be like K is 170,000. Okay, what happens is there is only one point, okay, namely this point, as we know now because we know the answer. When X is 300 and Y is, well, Y is going to be 600. At that point, okay, at that point, I'll draw this with a different line here. At that point, the level curve is going to only touch this point, touch the line, the red line, at one single point, okay? And that is the level curve where K is 180,000. Now, K could actually be bigger, like 200,000, but then it'll no longer touch G, right? So there is no point in doing this. And I mean, literally, there is no point where this area can be obtained as long as G is a constraint. Okay, so there is no point in drawing anything bigger than 180,000 because there is no point that such a curve meets the level curve G. All right, so the point here, the major point, and Lagrange's idea and his genius is found in this idea right here, okay? So in other words, you keep drawing these level curves, and the level curves, this particular level curve, right at this point, which is the answer, has to have the same direction as the level of the direction that's perpendicular to G, right? Okay, so the gradient, this is the gradient of F, okay? And so the gradient of F must have the direction that's perpendicular to G, all right? Now, of course, G doesn't have to be a line, okay? So in general, this is what's happening. In general, if G of X, Y is the constraint, all right, the picture would be more like this, okay? So G may have something like this, okay? This is the constraint, all right? And then you have the level curve, and the level curve could be blue, but the level curve of the maximum value, because it's a maximum value and there's only one point of intersection, they have to be tangent with each other, okay? You see what's going on here? Exactly, all right? So that means because at this point, these two smooth curves, I was gonna say two people, but these two smooth curves meet exactly at one point, they have to be tangent to each other. And so the tangential direction, the tangential direction has to be that which is the tangent line to both G and the gradient of F, which means then that the gradient, actually, I should not be writing this as the F. This is actually a level curve of F. Okay, so this is a level curve of F. But the gradient, which is perpendicular to the level curve, has to also be perpendicular to G, right? So that is the point. And that means the gradient of G is also going to be perpendicular and have the same direction as the gradient of F, right? So here's the point. At the maximum or the minimum, whichever you're looking for, okay, the gradient of F and the gradient of G must be parallel to each other, all right? In other words, the gradient of F must be some constant multiple of the gradient of G, okay? So the gradient of F is some lambda times the gradient of G, where lambda is some real number, okay? And I don't know why they use lambda. I guess lambda is a sort of a nice Greek letter that represents L as in Lagrange. Maybe that's why lambda is used. Okay, so this lambda is what we call Lagrange multiplier. it's a French name because he was actually a half French and half Italian. What a combination, what kind of food do they eat, Lagrange? What did he eat? Half Italian, half French, must be a great place. Well, I am making a stereotype. It's probably not a good idea, but it must be great to be half Italian and half French. All right, great wine they can drink every day. All right, so what do you do with this? All right, so here's how we apply this. Let's apply Lagrange multiplier, or the method of Lagrange multipliers, to this problem. Remember, G, the constraint was 2x plus y was 1200, okay? And f of xy was simply xy. That's the area, all right? And so we set this, the gradient of f is simply 2, 1, simple, no problem. The gradient of g is, what's the partial of, I made a mistake, didn't I? This is what I meant, but this is g. Okay, and this is f. So the gradient of f, the partial of f with respect to x is actually y, and the partial of f with respect to y is actually x, right? And we want to set this equation up. So what does that mean? I mean to say that yx is equal to lambda to 1, from which we get a system of equations. Y is 2 lambda, x is lambda. And the answer, of course, from this system of two equations, it's really easy to find the answer. Lambda is, y is 2 lambda, but lambda, x is of course equal to x. What I meant to say is x is equal to lambda. See that? Y is 2 lambda, x is lambda, right? So y is 2 lambda, which is 2x, okay? Now, we also have g of xy. So the gradient has to be equal to lambda times the gradient of g. All right, so that is the first requirement. The second requirement is that the constraint still has to be satisfied. And so that's 2x plus y is equal to 1200. Okay, plug this in to this equation, 2x plus y, which now we know as 2x, is equal to 1200, from which you get x is equal to 300, and y is of course 2 times lambda, which is 2 times x, 600. You got the answer, okay? And this whole thing is based on this exact fact here. The fact that was highlighted by this picture, which I will just highlight right here, okay? That the fact that g and the level curve of f have to have the same tangential direction, which means that their gradients have to be parallel to each other, which gives you this equation. That, along with the restriction or the constraint, will give you very simple answer. Okay, so you like it? I hope you do. All right, let me go give you another question and see if you can figure out this problem here. I am going to give you a question. Find the point closest to the origin on the surface 3x plus y plus 2z is equal to 7. Now, let me give you a little hint, okay? So the idea here is this. Now, this point 3x plus y plus 2z is equal to 7. So when x is, let's say 7, 7/3, is that it? 7/3, 0, 0. Is this a point on this plane? I think it is, right? Because if you plug in 7/3 into here and 0, 0 here, you get 7. Y 0, 7, 0, that's definitely a point on this surface. And so is 0, 0, 7 halves, okay? And so again, you can see this is clearly a plane, right? And so the plane with these 3 points, okay? So that's the plane that we're talking about. And what point on this plane is closest to the origin 0, 0, 0? Now, if I ask you to find the distance between the point 0, 0, 0 and this plane, you can use the method we learned back in chapter 3, and calculate the distance, right? I am not asking you to do that. I'm asking you to find the closest point on this plane, or the point on this plane closest to the origin 0, 0, 0. Now, what are you trying to minimize? You're trying to minimize. All right, now the distance between the point x, y, z and x naught, y naught, z naught is of course this. This is the distance, okay, from xyz to 0, 0, 0. But as you know, minimizing a square root function of 3 variables is not an easy thing. And so we always use this method. If you're trying to minimize distance, then you can minimize the square of the distance. Okay, it should make sense, right? Because if you're trying to minimize the distance, then trying to minimize the distance square is going to have the same result, because the square root function is what we call a monotonic function. If the square root of a number is bigger, then the number itself is also bigger. Okay, so we are trying to minimize this. Okay, let's call this f, which is we're trying to find the function x squared plus y squared plus z squared. That is the square of the distance between any point x, y, z and the origin 0, 0, 0. Okay, it is the square of the distance between x, y, z and 0, 0, 0. That's what we're trying to minimize. Subject to the constraint, and the constraint is, you have 3 constraints. Okay, so one constraint with 3 variables, and that is that x, y, z has to be on this plane, i.e. 3x plus y plus 2z, it has to be equal to 7. Okay, so that is my constraint. All right, so with this given function that you're trying to minimize and the subject to function, which is the constraint function, see if you can apply Lagrange's method to find the point closest to the origin on this plane. All right, and when you think you find the answer, you can come back and go to the second part of this video.